So I'm Dennis, I'm from Caltech. I'm going to talk a little bit today about some of the images I've encountered as a scientist there. And on my title slide here I have two images, one by the world-famous artist Angelenos, and another by one of the millions of lowly, unknown graduate students around the world. And I put these up here so we could admire their aesthetic value despite their incredible differences in scale. So the image on the right is a small particulate of matter, more than 1 million times smaller than anything you can see in the left-hand photograph. And it was taken with a very expensive, powerful electron microscope to which very few people in the world have access to. Scientists almost exclusively have access to these tools and techniques that allow us to peer into these hidden corners of the world that I'd like to argue can be just as beautiful as most of the things we can see with our eyes every day. So today I'm going to show a bunch of images we've obtained using all sorts of different scientific techniques. Some of these images are mine and some of them are my colleagues. So I come from Caltech, and at Caltech, Richard Feynman is somewhat of a rock star scientist there. He was a professor, he won the Nobel Prize, and he gave this talk about 50 years ago called "There's Plenty of Room at the Bottom." And in this talk, he outlined and basically predicted all of the things that we've very recently been able to do in terms of manipulating things on a very small scale. So the whole field of nanotechnology, this guy basically predicted 50 years ago before it was even close to being possible. So he was talking, of course, about science and technology, but I'd like to further that and argue that there's also plenty of room at the bottom for creating unique art. So I'm going to start with some microscope images, and the sheer scale of this is kind of fascinating. If you think about a camera and the kinds of images you can take with a camera, and consider the area of those images. Let's say you can capture around a couple centimeters to a couple meters with a typical camera. It turns out some of these microscopes can capture 10 to the 14 times more area. So how big is that? That means that for every photograph that you've ever looked at, there's about 10 million more times more area there to be explored in the microstructure, which is kind of fascinating. So first I'm going to show some microscope images, and we start with an optical microscope, which is kind of the most common type of microscope that everyone's probably used in high school or middle school. And these can magnify things about 10 to 1,000 times. So this first image here is from a researcher at Caltech, and it's basically of a rock, okay, a certain type of rock. But certain slices of material, or slices on the surface of this rock, are so thin that the light interacts with it and gives us these fascinating colors. Here's an image from one of my experiments. We were trying to make a very thin solar cell that was also flexible, so you could like roll it up and put it on your roof, for example. This particular cell, though, wasn't as flexible as I wanted it to be, and ended up breaking into millions of pieces. So here are 9 images from that failed experiment that I found under the optical microscope, and you can see these really interesting patterns that emerged from the film cracking along its crystallographic planes. Here's an image from another collaborator at Caltech. In this case, we were working on a solar cell. We were trying to put a layer of very small glass spheres or glass beads on top of the solar cell, and these spheres are supposed to interact with the light and help the absorption of the sunlight. And what happened here is that the beads didn't really distribute themselves the way we wanted. They kind of stacked up into all these different piles, and when it did that, it caused these fascinating colors. And so this is an example of what's called structural color. So the colors you see are just a result of light interacting with the geometry of the surface. So it's not from the typical phenomena that we think of when we think of color, like absorption by a pigment or something. It relates to the structure of the surface. If you looked at this from a different angle, or if you kind of changed the orientation of these small spheres, it would look totally different. An example of that is this image. It's the same exact thing, the same small spheres on a surface in a totally different distribution and under slightly different light, and you get a completely different, but still a very nice looking image. Okay, so moving on from the optical microscope, there's more high-powered microscopes that we use called electron microscopes. And so these are very different than an optical microscope. In an optical microscope, you collect the light that comes off of the sample. But because of that, you can only see things of a certain size, because light itself has a certain wavelength, a certain scale. So you can't really see things smaller than that. So an electron microscope actually works by shooting a beam of electrons at your sample and you kind of measure all the electrons that come flying back at you as it scans the surface. And you can see things that are much, much smaller than you can with an optical microscope. Let's say about 500,000 times magnification. So here are 4 images I took of an experiment where we had these very thin strips of gold, and we wanted these gold strips to roll up into like a sort of a Swiss roll type structure for various optical experiments. And some of them worked, some of them didn't. These ones all didn't work. They sort of unraveled into these random structures. But I found these very interesting looking patterns on different areas of this sample. Here's an example from a colleague of mine. He was growing this material in a high temperature furnace, and on certain regions of his sample, he found these really beautiful spirals of material, as shown here. Here's another image of mine of a thin film of metal that was deposited onto a plastic, basically. And after we deposited this metal, I heated it up for various reasons. And when you heat things up, they expand, and different materials expand at different rates. And sometimes when that happens, things start to peel up and crack. And so the gray areas that you see are the metal that was stressed by the heating of this and caused these interesting patterns. Zooming in on one of these, we get this image, which is one of these metal films peeling up, and you can kind of see the pattern on the back of the film, which has its own striped type feature as a result of its interaction with the material below it. Okay, so it turns out you can even keep going further down in scale and up in magnification. There are these things called transmission electron microscopes. They're similar to the scanning electron microscope, but a little different. You're able to get to, let's say, about 1,000,000 times magnification, which is really small. And so here's an example of one of my images from a sample of just a couple of pieces of material of an oxide, which is kind of like rust, nothing really exciting, and some pieces of carbon. And on this very small piece of this sample, I found this image. Here's another transmission electron microscope image from a researcher at UCLA. And you can see, in this case, it resembles these flower-like patterns. Okay, so we don't just use microscopes in our work at Caltech. We also do a lot of calculations and simulations. And so now I'm going to talk and show a few images from these types of, using these types of data. So here is a composite of 20 images of a simulation of us looking at how light is emitted from a point in space. So kind of like how an LED emits light. We can simulate that. And each frame of this is a different moment in time. And we're looking at a plot of the electromagnetic field as time evolves. So there's a lot of scientific information in this showing us how light is emitted from a point in space and how it interacts with its environment. And it also makes a very nice image. Along the same lines, here are 2 more images of electromagnetic simulations, so of light. And the image on the left is actually one of those small glass spheres I mentioned earlier. So we did a simulation, and you can kind of make out a circular or spherical region in the center, and there's light coming in from the top, and we're plotting the electromagnetic field and how it interacts with this very small structure. And on the right are 16 images of light. Again, light, this time trapped between 2 square plates. So we have 2 plates of metal, and we look at how different wavelengths of light distribute themselves when confined to this geometry. So each of these panels is a different wavelength of light, and it orients its fields differently depending on its wavelength and the geometry. Okay, there's also a lot of really nice work at Caltech working on fluid dynamics. So they study how fluids flow, like water, other things, air is a fluid. And here are 2 examples of this. On the right is a liquid, excuse me, on the left is a liquid with some agitation, and depending on the agitation, it forms different patterns. And on the right, actually, is an image of an eel swimming downward. You can see the black area in the middle here is an eel, and they're simulating the patterns in the water behind the eel as it swims. So these things exist all the time out there in nature. We just can't see them with our eyes. It takes these kinds of simulation tools to really see the beauty in it. Okay, before I close, I'm going to switch up a little bit and talk about something a little different. that I've been doing at Caltech with some friends, sort of just for fun. So it doesn't have that much scientific value at this point, and it's called generative art. And so generative art is a little hard to describe, but the best way to describe it is that the artist or the person that comes up with the piece, they set up a system or a process, and then they sort of just let it evolve and just kind of sit back and watch it and choose what they like. And the simplest example of this is a set of wind chimes. So somebody cuts out these wind chimes, each one, they determine the length and the note, and they sort of put it in the wind, and they let the wind just play it. And so you can't really predict the wind, it's very random. There's always a random element usually in this type of generative art. And you just sit back and listen. And it sounds good because the person who made the chimes chose them to all be notes that go together. So the first visual example of this that I know of is from this guy, Desmond Paul Henry, and he made this thing called drawing machine, where he basically took a bunch of gears and strings and attached them to pencils, and he ran this machine that would draw these really nice images like you see on the right. Then if he changed one of the gears slightly, or if he changed one of the lengths of the string, he'd run it again and he got a totally different image, but it would still look really nice. So this kind of leads to my favorite definition of generative art, which is generative art is when you lose control of a machine that does exactly what you tell it to do. So you program all this in, and you sort of let it run. You don't really know what's going to come out, and sometimes you like it, and sometimes you don't. So, of course, today we can do things much more advanced than this drawing machine. We can do things with computers. And so here's an example of kind of the same thing as the drawing machine, but with a computer. And so in this case, we have a computer program where we set up a three-dimensional space, and we tell the program to draw a dot with a certain color, just a single dot. Then we tell it to rotate that dot around 3 different axes and draw another dot. And then we do that many, many, many times in the computer. And depending on the parameters we've put in for the rotation and so forth, you get different patterns. So here's an example of one pattern you get iterating this process many times in a computer, which of course happens very quickly with today's computers. Now, if you go and change one small part of the computer code that does this, you can get totally different images, for example, something like this. And so when you go in and change a part of the code, you usually don't know what's going to happen, really. You just sort of change it, and then you sit back and watch and see what comes out. And sometimes it looks good, and sometimes it doesn't. Now, here's another example of kind of the same things, but instead of printing dots, we printed basically small rectangular units. And again, you get very different looking images. Okay, so we're gonna do a little math here, so don't be scared. It'll be quick and painless. But I want to do a simple example of generative art and sort of a mathematical art thing that we did at Caltech just for fun, just me and some friends. And so this equation here is one of the simplest equations that exhibits chaotic behavior. So you've probably heard of chaos in terms of the so-called butterfly effect, or the fact that a butterfly flapping its wings on one side of the world can somehow influence the weather on the other side of the world. And so this is just a way of saying that some things are so complicated you can't predict them. Any small change in the initial conditions or when you start looking at everything can have a very different effect on the end. So anyway, this is a very simple equation for that. We wanted to look at it and try to just make some nice images from it to maybe bring people to the math if the images were nice. So this is a very simple equation, and what we do is we start with a number, r, and we choose a value for it, and then we choose a value for x. And then we just do this simple mathematical process, which is a subtraction and a multiplication. And then we get a new number. And then we get the new number and we put it back into the equation, and we do this over and over. And so if we do this 100 times, you end up getting a number. And if you keep doing it, you keep getting the same number. And so then we're going to plot this. And we plot it here. We have 1 point. Okay, that took 100 calculations to get that 1 point. Then we go and we see that it never changes after 100. Then we go and we change one of these numbers we started with. And we do the same thing. We do it 100 times. Turns out after 100 times we get 2 different numbers. And if we keep going, it jumps back and forth between these 2 numbers. Okay, so this is getting kind of boring, right? So then we tell our computer to just do it really fast, okay? And so the computer does it over many, many different times. And you got to plot like this. And so this shows the same thing, but at a much better resolution. And you can see farther along on the graph, around 3.6, you can see something different happen, where no matter how far you go, you can't really predict what the number is going to be. It's very unpredictable. Where on the left-hand side, you know you're going to get one number or two numbers. And so this is an example of chaotic behavior. And so we did this because we like the math, and then we tried to make some images out of it. And here's an example of one that we did, taking this calculation and manipulating it and copying it and trying to make something that looked nice. So it kind of loses its mathematical value at this point, but it kind of looks nice and maybe will attract people to the math behind it. Worth noting on this is the image on the right, every dot of color, every single pixel is a result of 100 or more calculations. So there's lots and lots of calculations that go into this. And of course, the computer does this in a few minutes. And with that, I would like to conclude. Hope I've convinced you that there's a lot of room between science and art for interesting things, and scientists have some unique opportunities to discover some of these beautiful areas. So thank you very much.